Hi, welcome to the Signal Path. Today we're going to take a look at this broken HP oscilloscope. This is an 54845A 4-channel oscilloscope, and this is one of the last units which was branded HP, and after this I believe they started branding the Infinium oscilloscopes with Agilent, and now of course with Keysight. Now, even though this is a fairly old unit, it still has very impressive specification. First of all, it's 4 channels as you can see. Second, it's a 1.5 gigahertz, 8 gigasample per second oscilloscope. Now, except for the S-series scope, which is in my lab, the Keysight one, which has 8 gigahertz of bandwidth, this is now the second highest bandwidth scope I have, because I have a whole bunch of other scopes that have a 1 gigahertz bandwidth. So it's a really quite an impressive and quite a useful unit. Now, this one runs Windows 95, I believe. And it has a couple of problems. First problem is that nothing shows up on the LCD screen. And even though nothing shows up on the LCD screen, whoever sold this must have been able to test it using the VGA connector at the back of the unit, because the second problem, which is actually the more problematic one, is that it randomly and fails a self-test. So sometimes it passes, sometimes it fails, which is quite unfortunate, because that kind of intermediate problem is difficult to trace. Now, I'm generally very reluctant on picking up oscilloscopes that have problems, because if the acquisition board is bad, there is really not much you can do, because all the ASICs, including the ADC, are all custom, and if you were to replace those, you have to replace the whole acquisition board, and in that case the whole value of the oscilloscope is in that board. But nonetheless, it should be interesting to take a look, because the architecture of an 8 gigasample per second oscilloscope, 1.5 gig bandwidth, so long ago, should be very interesting to take a look at, and you will see how the architecture is different from how they build scopes today. And a lot of things have changed in order to build high-speed ADCs and also high-speed oscilloscopes, acquisition systems. So if you go and look at the teardown I did of the Keysight S-series scope, then you can compare it with this one and see how far they have actually come in the development of these things. So it's pretty awesome to take a look. Now, as you know, all these Infinium oscilloscopes have all dedicated knobs and everything, which is great, and they're all color-coded and everything, and the triggering is really straightforward. They have kept this feel and this style even all the way to their modern oscilloscopes and Keysight and Agilent, and I'm very happy with it. This one has a floppy disk and a regular hard drive in it, no SSDs of course back then, but nonetheless very cool. So I have already plugged it in, and we can turn it on and see what it does. So there we go, it cranks up, and yeah, nothing seems to be showing up. Oh, there we go. I think that's about it. Now a whole bunch of the lights are on here, or not much activity, but it has to boot. But as you can see, nothing is showing up on the LCD screen. Now these things, like I said, run Windows, but as soon as you push the button, it turns back off. So they have taken care of to make sure that the OS recovers from this type of activity the user may do. But nonetheless, I thought, what a better way to start than to take it apart and see where the LCD is connected to, and also everything else that's in there. That should be a good place to start. And here we have the unit. I just took the top cover off, and we're looking at the top of the unit. So this is the front of the unit, this is the back, and you're looking at everything that handles the PC basically. At the very top, we have quite a large power supply rated at 500 watts, quite a bit of power required to run the ASICs. You can see some of the connectors here, all of them going to the other side of this board where they feed the main acquisition board. And we'll take a look at it when we flip it to the other side. Now, the motherboard that you see at the far back is the main motherboard that has the PC components on it. There's an x86 processor all the way down there behind this block, which is the floppy disk. You cannot see it, but it has a little tiny fan on it, and again, doesn't need to have a lot of processing power. It is, after all, running just Windows 95. The main hard drive, which contains the OS and everything, is over here. This big block that you see here with a heatsink on it is actually a voltage regulator, and it's rated at 7.5 amps, probably one of the main voltage regulators for the motherboard. Now, one of the interesting things about how Keysight has done this is that they have designed, they used to do their own little PCI bus cards, which handled all of the IDE interface controllers, handled the acquisition card interface, and even the front panel buttons. Everything used to go to those cards, and those are these two cards over here. So this top card over here is in fact connected to the floppy drive, to the hard drive, so ID controllers on that, and also probably, oh, actually, you know what? At the very back, I remember seeing that. There it is. You can see over here the VGA port that it connects to the monitor is actually there too. So the video processor is in there as well. And this ribbon cable that you see coming from the other side is coming from the acquisition board. And all the data from the acquisition board interface, the digital data, comes to this other board, which is then captured and processed. And you can see there's a bridge between these two cards, as well as the fact that both of them are directly sitting on the PCI bus of the main motherboard. So this is how they capture data. If you remember my teardown again from the Keysight S series, their acquisition board there sits on the PCI Express card before all the data is processed in some custom design algorithms in either ASICs or FPGAs, and this is what they do here too. So this is the same style, same overall architecture that's been developing over many years before it's reached this state-of-the-art oscilloscopes they have now. And this motherboard is so old that it even has ISA slots, which I haven't seen in a very long time. This part over here, I have no idea what that is. Could be an Ethernet, could be, let me take a look. That is, yes, that is an Ethernet card, and the one underneath it is a GPIP controller. So everything kind of makes sense. The architecture is quite clear, and it looks quite nice. So if I were to look around, and oh, you know what? I just realized something. You know what this is, right? Of course you do. This is our LCD controller. This is our LCD port, and it has come out. That's why the LCD wasn't working. Again, I was expecting this to have a very simple problem because apparently the VGA port is working. So we're going to hopefully plug this in, and I am hoping there is no tear in it. It looks okay so far, and we'll plug it in and see if the LCD comes back to life, and then maybe we can try and tackle the main problem, which is the problem of this intermittent self-test failure. I actually haven't plugged in a VGA at the back, but I'm assuming it's working based on the description that I saw. So let me give you another closer look over here and see what it looks like, maybe a few closer components inside the unit. And here is a closer look over here. In case you're wondering, like I was saying, this is the acquisition ribbon cable. In fact, I should be able to remove it. There we go. And you can see that this ribbon coming out of here is controlling the backlight for the LCD screen, and this is the main ribbon for the LCD screen. So let's see if we can put this guy back here. Hopefully. It doesn't seem to be going in very well. Oh, there we go. I think I may have gotten it. Now we can push this guy in there. This camera is in the way, but I think that it is okay. So there it is. And now we can plug this guy back to where it was, and hopefully this will correct our LCD problem, and then we can start tackling the main problem, which is the intermittent acquisition failure. So everything else looks pretty good. There's the x86 processor I was referring to before with a fan right on top of it, most likely just a regular Intel processor. Maybe when it boots up you'll see it. Here's an interesting module here, which seems to be a power supply module for controlling the processor. Probably they designed this in order to be able to put a different one depending on the power supply requirements for a specific processor that they are installing. So they've kind of made this weird module thing where the power supply controlling all the requirements for the CPU is not actually on the motherboard. Well, it's a little bit unusual. Again, just like the older HP, it's a bit of a hack together. It's not as elegant, as nice as all the new ones where everything just mechanically plugs into each other with no connections, no ribbons. This is ribbons all over the place, but that's okay. It still should be fine if it works, and I'm very eager to try it out. So let's look on the other side. And here's the back of this monstrosity where you can actually see the complete acquisition board. And immediately you should be able to detect some of the major differences between how oscilloscopes are built today and how they were built back then. One of the reasons that this is different is because the technology to be able to build very high-speed traces in a controlled way and calibrate them out and have integrated circuits that can accommodate some of the limitations of that was that they wouldn't put the traces, your high-speed analog traces, on the PCBs. They would have isolated module built from much higher quality components at the time that would give you a much better performance. And that's immediately apparent because these are all your 4 channels that are at the front of the instrument, and you can see channel 1, 2, 3, and 4 are actually traced using a coax cable as opposed to being on the PCB. And these are not just ordinary coax cables. I believe these are filters built into the coax cables like we saw when I did the repair of a spectrum analyzer, and these filters are likely there to provide proper anti-aliasing and to filter out noise at the higher frequencies, which would not be necessary before the signal is fed onto the ADCs. So the ADCs are clearly here, 1, 2, 3, 4 ADCs. And these are 4 gigasample per second 8-bit ADCs, and there's 4 of them, and which means that if you want to get 8 gigasample per second and have 1.5 gigahertz of bandwidth, only 2 channels can be active at the same time. And given the fact that 2 of the channels come from the same front-end module and the 2 other ones come from another front-end module, it means that once you enable 8 gigasamples per second, the second channel is disabled and the first channel is then routed to both of these signals. And the same with this one, channel 3 is routed to both of these signals, and channel 4 is disabled, and then these 2 ADCs will work in a time interleaved fashion to give you 8 gigasample per second. And I'm guessing that that's what we will see if we were to boot it and take a look at the menus in the acquisition and configuration. There's couple of other circuitry over there. There's one over here and one over here, which are both seem to be custom and likely responsible for trigger portion, because these things did have dedicated trigger functionality. It's not like now with the Keysight where everything is handled in the digital domain. The trigger circuitry is typically not done in the digital domain in most of the oscilloscopes. And here we have the crystal oscillator, which is a Vectron part. It's actually a 2 gigahertz oscillator, and the reason they went so high up is because, again, they couldn't build a PLL at starting at a much lower frequency reference in order to be able to feed the 8 gigasample per second ADCs with a very clean clock, which of course determines the effective number of bits of the ADCs very closely for higher input frequencies. So all of that makes sense. The architecture is really straightforward. And the data that is collected by all these ADCs processed and then passed on through the only interface to the main board on the other side, which is the motherboard, and collects and processes and displays the data. There's a couple of other interesting things to note. Look at all the different power supply voltages required to run this board. It's quite amazing how much stuff is required to feed all of these analog and mixed signal circuitry over there. There's an interesting little module here, perhaps with some firmware for everything that's on that board. The trigger function from there is fed onto the motherboard using this little portion over here. These 2 boards are connected to the motherboard with vertical connectors, and they can be replaced. And on top of them it says channel number of cycles used. Is because there are attenuators and relays and switches built onto the front end. So if you were to replace them, you have to say how many times those have been used so that you can keep track of the age and the changes in the front ends as time passes. That's why they have that. And also this ribbon that you see over here that goes right underneath connects to all the probes DC connectors. So if you plug in an Infinium probing system onto here, the probe needs power, the probe needs an I2C interface to communicate with it. All of that is handled through this ribbon cable, and there's a board up here mounted on the side, and that board has a whole bunch of voltage regulators and minor digital processing on it to establish communication with the probes, and that's how the probe is powered. So that's actually a separate board, not on the main acquisition board. But you can see it looks pretty straightforward. And now, so the question is, why is it having an intermittent failure? Well, it could actually be a mechanical problem, because these things go through a tremendous amount of thermal cycle, especially the interface between the ADCs to the board themselves, because looking at the side of this, over here, I can see that these ADCs are actually socketed, which is very interesting. They're not soldered onto the board, and one of the reasons that's the case is because their yield must have been terrible. So they've done this to be able to replace these ADCs and not have to build an entire acquisition board and then find out, oh, the ADC is bad, we gotta toss it out. So they actually have to self-test these, calibrate them perhaps in a jig, and then put them on here, and that's the only way they could get any reasonable yield out of this. And same comes with the front end analog portion, which handles the attenuators, the scaling, and all that. Another interesting thing to note is that the signal going into the oscilloscope, into the ADCs, is still single-ended coming out of here, meaning that single-entity differential conversion is accomplished directly onto the ADC hybrid package here, and I'm very eager to see what's going on. So let's turn it back on and see first, before we do anything, is if the LCD screen is now working. And these 2 huge fans that you see here blow air down. So if this thing does not have a cover, which will have it when the case is closed, the air flow will not go over these heat sinks, and these things will overheat. So what I will have to do is basically face it down on the table and have the table act like an air conduit, allowing the air to flow across these and cool them down. But other than that, I think it looks pretty nice and fairly straightforward in terms of its overall architecture, and a state-of-the-art at the time that it was built. These little red things that you see, these pillars are standoff pillars, so when the case is on top of it, that it won't get pushed down and crush any of these things. It's basically just spacers, which is quite handy when I'm going to put it flat on the desk, and that will also protect it. So everything looks good so far. Let's go and plug it in and see if it comes back to life. All right, so here we go. Let's give it a try now. Oh, of course, it would help if I actually plug it in. That would be a step forward. Sorry about that. Here we go. Plug it in. Now we can try it again. Ta-da! Let's see now. Come on. Show me something. Oh, that's different. Ah, there we go. See? There it is. It came back to life. You see, I'm really earning that PhD degree right now, plugging cables back onto boards. And it looks good. So damn it, I missed the actual processor that was there, but it has 16 megabytes of RAM. It's a beast, all right. And you can see all the different kind of PCI cards that are plugged in. You see there was some USB controller plug that was there, and it's asking for a password. Well, that's a little bit unfortunate. Okay, well, let me figure it out and see how we can get into this, because I don't actually have a password. Let's see if we can bypass this. Alright, I managed to get into the main operating system, and the actual software of the oscilloscope is now running. And even though it looks perfectly fine right now, just a moment ago it was giving all kind of trouble. There were random spikes that would show up on a couple of the channels. They would come and it would go away. And now that it's warmed up, I can see it significantly stabilized. And of course, now that I'm recording, none of the spikes are showing up again. And then I ran the self-test from the utilities menu, and the first time, just as soon as it powered on, it failed on 2 of the channels, and then now that it's warmed up, it only failed on 1 of the channels. So I think it might be what I was mentioning before. There might be some simple mechanical problem there, some connection not being made. So what I'm going to do is perhaps we should take those ADCs out of their socket, take a look at them, clean them up a little bit, and make sure that they are making good contact. The sockets, those are quite high power unit, and it may be that there is some interface integrity problem because of all the issues. But you'll recognize, if you ever use these old scopes, that they look, the very, very classic old Infinium interface, and this is the evolved version of this interface is the one that's used on the new scope. So let's go ahead and power it off, which I think you just have to push the button. It's kind of scary running Windows, but anyway, so now we're gonna take a look and see if we can fix this issue. And here we go. I took one of the heat sinks off, which are simply screwed in with a couple of screws, and you can here see a thermal pad there that makes connection directly to the back of that package. And this is an expensive package. I mean, we're talking about a ceramic custom cut package with a connector directly on top of it, soldered onto the ceramic piece itself, with a cut through, which on the other side I'm assuming is where the main ASIC is, and this is screwed in onto the PCB one other time. So they really went all out when they were designing this. So let's take a close look at it. And again, because this is a very expensive oscilloscope at the time, cost was not an issue. This thing must have cost an arm and a leg. Now this scope like this is a couple of thousand, no more. So let's go ahead and now remove one layer further, and I want to make sure that I remove this in the right order, because I like to be able to save it, and so that we don't break it, because it's most likely just a connection issue. So I'm going to take all the 4 screws out, and then we have to make sure that we disconnect the connection directly to the unit very carefully. Now these cables are in this particular shape, so they can be bent like a spring, and be able to remove them without having to shift this around, because I'm not so sure if this can be removed after I take the cover off. Then it will be loose, and I don't want to disturb any pins which may be there, although I don't think it has any pins on the package, but we'll find out once I take it off. So let me play around a little bit with it, and we'll continue. And here's the successful removal of our coax filter piece over there. So now one more step. We are almost there at the point of being able to get the whole package out. Alright, here we go. The screws are off, so we should be able to take this out. And this is of course all custom pieces. I mean, take a look at this. This is made specifically for this purpose, just to hold the ASIC ADC onto place. This is a completely machined piece of aluminum just for the purposes of this particular design. And furthermore, you can see that at the very back we have a plastic piece that is connected to the PCB itself. Now I suspect that this will completely come out in one piece, and you can see there are 3 alignment pins there. So let's see if we can get this out, and it should be there we go. Yeah, it's coming out, and here we go. Ta-da! Just as I told you, no pins at all, just to be expected. and take a look at it. So you can see that there are pads all around here, and those pads connect to the A to D converter that's inside, and those data will all be digital, the digital channels coming out for the various conversion bits and so on, all coming out and getting processed and collected from the external circuitry. Now here's the analog input. You can clearly see that it goes inside underneath this cap, and under the cap we may have multiple dies or just one die. I'm not sure, most likely more than one die is present there. And you can see a few other very tiny passives right over here, but all the other components were going to be completely blocked off. And on the other side we have the heat sink where the main data converter would be and getting the heat out. Now this is ceramic, not just that, it's two pieces. It's gold plated with the traces on it. They have spent a ton of money making these ASICs the way they are. So this was a very expensive unit, as I was mentioning, but that's to be expected. This is low volume, very high price. At a time, very fast data conversions. And this piece over here is interesting as well, because it's just an interposer to create an interface between the ceramic package pads and the PCB itself. So there are pogo pins sitting all around here which press against the pins on the ceramic package itself, and that's how the communication is made. And this is where I suspect the problem actually lies. And this is, again, with the thermal cycle going in and out, probably the connections are not being made very well. So I'm going to have to clean it up and clean the package as well and reassemble it, and hopefully that will solve that problem. And you can see some traces over here, in fact, coming from this, and I suspect that obviously is the clock. And since this is 2 gigahertz and this is 4 gigasample per second, there's either two ATDs in here, time interleaved yet again, or the clock is multiplied internally. Most likely this is time interleaved internally. So very interesting. I don't know what technology this is implemented in. I haven't looked at the service manual, but I will check and hopefully post it in the comments, and we can go from there. This is HP branded. Very cool. Very neat. Again, this is very modular. They have no choice because they couldn't solder these on, and it would be a whole bunch of other problems if they did. So let's go ahead, clean it, assemble it back, and then I'm gonna have to do this 3 more times for all the channels, very carefully cleaning and reassembling, and then we'll turn it on and do a cold boot and quickly jump directly onto the self-test and see if that problem actually goes away. Okay, well, I did what I could. I cleaned them as much as I could and realigned them and put them back together and closed everything up, torque wrenched everything, making sure everything was at the right torque, and then connections look good, and it looks back like exactly what it was before. So now the question is, will it go through calibration and self-test correctly? So let's turn it on. Well, that's kind of promising. So I ran the self-test immediately after it turned on a couple of times in a row, and it passed every time. So, and I actually haven't seen any of the spikes that were showing up here, the little impulses, and anymore. Even though immediately when I cooled it down, I sprayed it with some cooling gas, and nothing. It doesn't do that anymore, which is very, very nice. And this was one of those situations where you could be chasing something for a very long time if you haven't thought very carefully about how this is put together, and try and correlate the behavior that you see with the way this is assembled and the way the architecture is. So this happened to work out quite nicely this time, and I think it's fixed, but of course we have to put some signal through it to see how it behaves, and I'm curious about what it does near the 1.5 gigahertz of bandwidth. Now, as I was saying before, if I go under setup and acquisition, and in fact you can see clearly, I don't know if it shows up very well on camera, but if you select 8 gigasample per second, it will have 64,000 points of memory distributed between the two ADCs, and it will be channel 1 and 3. So if I do that, then my channel 2 will be completely disabled. As you can see, the light is not taken off, so only channel 1 works and channel 3 works. And if you select 4 gigasample per second, then you have channel 2 and channel 4 also available. So that makes sense. It's exactly what I was saying before. It fits exactly with the architecture as we saw in hardware. And it also has a 9-bit bandwidth limit mode, which only works up to FS divided by 20. So if you're at 8 gigasample per second divided by 20, and that's the maximum bandwidth you will have. And this is done obviously by oversampling and filtering. So that's a typical thing that people used to do when they weren't building higher resolution ADCs, and they still do when they want to get a little bit more resolution with oversampling, which is not very efficient in Flash A2Ds, as I've done a tutorial on that before. Make sure you check the tutorial on Delta Sigma data converters. So anyway, let's go ahead and connect some signal into here and see how well it works. Alright, let's put some signal in there. And on channel 1, let me change channel 1 to be 50 ohm, and there it is. And Look, it has little lights for all of the settings right on the front panel, so you know it's DC coupled, you know it's 50 ohm. This is really important because otherwise you can damage it if you put more than 5 volt RMS into it when it's in 50 ohm. I love it when they used to have these little lights in the front. Anyway, so let's go ahead, enable our 100 megahertz signal. It's 100 megahertz, at what is it, at 0 dBm, that's tiny. Let's go ahead and change the vertical. There you go, it seems to work. Let me turn all the other channels off that we don't need. And yeah, there it is. It looks good. I think it's correct. Let's do a peak-to-peak measurement. And there it is. Yep, 623 millivolts or so. That's exactly correct. And the frequency over here, it should be 100 megahertz, and that also is correct. Now, as soon as I enable any measurements, you can see that the screen update rate drops significantly because it didn't have enough processing power. Not all the processing is done in hardware like it is in a modern oscilloscope. Some of it relies on the software, and that's why it's a bit slower. Let's go ahead and increase the frequency, 200, 300. By the way, let's see how well it does with aliasing. Let's go this way. And oh no, it doesn't do a very good job. It's all confused now. Oh well, it's okay. Let's continue on back to here. Now we're at 200 megahertz, so let me go all the way. You can see the signal already becoming smaller. This is 1 gigahertz, and let me actually change the acquisition mode to 8 gigasamples per second. There we go, to make sure we are really getting all of our bandwidth. And 2, 3, 4, and 5. That's 1.5 gigahertz. You can see, it cannot trigger very well anymore because the trigger bandwidth isn't quite as good as 1.5 gigahertz, so it's having trouble triggering on that. And again, this was something that was characteristic of the older oscilloscopes. Is to be expected. They can't keep up at the very high input frequency. And if I go any higher, you can see that first of all there's a significant attenuation, and then we're beginning to have completely loss of triggering. So let me go back down to a 500 megahertz signal, which looks fairly reasonable, and let's try the other channels and make sure it works. Let me go back to regular 4 gigasample per second acquisition, and here I can turn channel 2, 3, and 4 on. I can put all of them into 50 ohm. Seems to be good, everything clicking. And let's jump to channel 2. I can get this out. Channel 2. I gotta change all the vertical. All of them have to go to 100. Oh, interesting problem here. This knob doesn't do a very good job. Let me turn it a few times here. I think it had some oxidization on it. There you go. It's a little bit better. And 100. There. Now the trigger can also be changed. The source, channel 2, looks good. So far so good. Channel 3, come on. Very nice. Also good. And finally channel 4. And channel 4 looks good. I think it's definitely functional, and it seems to be working. I don't think there is any problem with it. Now, at least, doesn't seem to have that banged it around a little bit, tapping it and so on. I don't seem to be able to cause any problem, so I'm pretty happy with it. I should say that it is working now, which is quite nice. You can see connected to channel 4, and yeah, very good. So anyway, I know it seemed like a simple problem, but this is one of those situations where if you're not thinking about it very carefully, if you don't have experience, you could be chasing something for a long time. And hopefully this was handy, and then you can see the architecture and how it's built and look at the package of the ADC. And I hope that you found this video beneficial. My next one will be a review that I have been working on. It's quite an exciting one also, so I hope that you enjoyed that one. Until next time.